Well, hello. Hey, let's go through section 4.3, where we're working from the Riemann sums that we have been doing and into an integral. And we have some experience with an indefinite integral. We know that if we integrate this, we would integrate, whoops, what am I doing here? Where I would integrate, I don't want an integral sign anymore. I would integrate x to the third divided by 3 plus 5 bring on an x plus c. That would be the antiderivative of that. Well, what we see over on this one is I have bounds. So that's what makes this a definite integral. These bounds tell me where I'm looking at for the value of my integral. So for instance, maybe I'm going 0 to 2 here of this function, negative x squared plus 5. So what it's asking is, how much area is contained between an x equals 0 vertical line and an x equals 2 vertical line, and then under the f of x function. So that's where we're headed. Oh, I see there's a question here. Is this a left-hand or right-hand Riemann sum? We'll look at it for a minute and try to determine what set the height of the rectangles. And what I notice is here's the intersection point, which is on the left side of my rectangle. So this would have been a left-hand Riemann sum. Okay, so like we discussed, we're moving from a Riemann sum into a definite integral. What I want you to do is just draw in a few things. Let's just give ourselves some function. All right, so some function, I'm going to call this y equals f of x. And we know that when we do the Riemann sums, we sketch in, I'm going to make mine a midpoint one. We sketch in a rectangle, and this height, which was y equals some f, evaluated at an x value. What x value was that? Well, I'm going to call this x value c sub k. So I would find the height by looking at my function evaluated at the x value, c sub k. That would produce then for me, this side would be x equals, or an x value that is 1 to the left of k, and this x value here would be k plus 1 unit for my evaluation, or c sub k minus 1 and a c k plus 1 if you wish. So this determines our height, and then I have some width here. And if I take and subtract these, I would end up with some x that is k change of x sub k. So we'd have a difference of our x in the kth band, if you will. Okay, so that gives me delta x sub k. Well, working off of that picture now, we can maybe produce some things. To estimate the area bounded by the graph and the x-axis between the vertical lines, x equals a and x equals b. So maybe we should add, I hate to add one more thing, but let's call this x equals a. There's my vertical line, x equals a, and then x equals b. What we'll be doing is we'll be trying to calculate the total area under the curve between x equals a and x equals b. We'll partition the area into sub-intervals, just like we were showing here, and then we drew a general point within that sub-interval. Not necessarily left or right, but just somewhere in between, and that's how we came up with our x equals c sub k. Now, the area of our rectangle is going to be the width times the height. Makes sense. And in our picture, our width we call delta x sub k, somewhere where k fits between a and b. And then our height ended up being the function evaluated at c sub k. And then we just have to multiply those together. The sum of all these rectangles, so imagine, densely packed rectangles in here, will give us a summation where k is equal to 1 to some number n, depending on how many rectangles we make. And what I'd want to do is sum all of these width times height. So I'm going to sum up delta x sub k times f of c sub k. And if I do that, I will get the area under the curve. Now, we qualified that our c sub k was sitting between, and you can see it on our picture, so the x values were k minus 1 to the left and k plus 1 to the right. When we do this summing, this is called a Riemann sum. How can we get the exact area under the curve? Well, to do that, we would just want to allow delta x sub k, that change of x, to go to 0. We want to make very skinny partitions. Oops, not skimmy. Skinny partitions or subintervals. And lots of them, so that I just densely pack this with skinny little rectangles instead of big fat wide ones. Then we come into the definition of a definite integral. I know this kind of seems heavy, you guys, and we will have to do some interpretation of this, although that's not really the focus of today's lesson. But we've got to have this background information. So what got added on this definition of a definite integral? Definite because I see the bounds. Well, the main thing that I'm picking up here is this limit. Do you notice that? We got a limit as n goes to infinity. Up here, we talked about the fact that we want to sum up all these width by heights, all these little areas. Now what I'm going to do is say, I want to take and do infinite number of subintervals. That means our delta x sub k is really, really skinny now, okay? Because we're taking and making lots and lots of partitions. That becomes the definition for a definite integral. So hopefully that kind of makes sense to you. So region, definite integral as the area of the region. We talked about how it's bounded between A and B. That's your bounds. It's under the curve because this curve generates the height for us. And differential x, I talked about this yesterday with a couple classes, maybe not every class. The x, differential x, is the width. Differential x is super tiny. It could be referred to as change of x, but differential x is super tiny thin, okay? So we get height times width. We want to sum it. It turns into really a definition. That's a limit definition, which is why chapter 1 was so critical to us. Learning about limits, because calculus, you can see many things are defined using limits. Here we hit theorem 4.5 out of our textbook, the definite integral as a region, area of a region, kind of repeats what we've just talked about. But this other one here, and I don't know if I can make it larger. It says, if a function is continuous on the interval, the closed interval, then f is integrable on that interval. So we know how we had differentiable, and if a function was continuous, it's differentiable. Now we also pick up if a function is continuous, it's integrable. Alrighty. This particular screen is indicating that when I have a function that lies under the x-axis, that this area is picked up as negative area. Meaning it's going to take on a negative value, really. I mean, it's really kind of sounds weird to talk about negative area. Think of it more like a negative value. This has positive value. So above the x-axis is positive value, below the x-axis is negative area value. Integral notation, we've gone through quite a bit of this, but you're going to talk about this being the upper sum. Upper kind of implies that this should be the larger number, shouldn't it? And then lower seems to imply a smaller value. So I want my smaller number on the bottom and my larger value on the top. If it isn't that way, we have ways to deal with it to flip it over. We'll talk about that. We know this differential x is there to help also show us what variable we're integrating with respect to. And then f of x, of course, is our function determining the height of the function. So, enough background. Let's just get down and do this stuff. Sketch the region of the curve corresponding to the definite integral. Then evaluate each integral using a geometric formula. So they're introducing this in a very soft way of getting used to what does this mean, what does this mean, and then how can I evaluate it and come up with an answer. Well, I know if my function f of x is equal to 3, that's like saying y equals 3, which is a horizontal line, correct? So we're going to plot a horizontal line at the height of 3. And I'm just going to say this is f of x equals 3. My bounds indicate that I have x equals 1 and an x equals 4. So let's plot our bounds as well. Let me grab this. Our bounds, x equals 1, x equals 4. Now the region that we're interested in is this region here. Please shade it in. That is what this integral is asking us to do, is find the value of that area. Well, that's pretty easy, isn't it? I have 4 minus 1. I have 3 units wide here, and I have 3 minus 0. I have 3 units tall. So this calculation will turn out to be 3 by 3, which gives us a value of 9. Easy? I think so. The next one I see I'm going to be bounded from 0 to 3. You could plot those in if you want. 0 to 3. And then here is my function, 4 minus x. So that's a linear function this time. Let's go up to 4, which is our x-intercept, and then count down by a slope of down 1, right 1. Connect up my dots, shade in the region that we're interested in. We are interested in this region. Not quite a triangle. It's a trapezoid, isn't it? You know what I think I'm going to do? I'm going to count squares. 1, 2, 3, 4, 5, 6, together 7, 7.5. Just getting the geometry under that curve. All right, C, for C, that, okay, just so you recognize this function, and maybe some of you do, what would happen if I square this? Right now I'm picking up only the positive portion of this, but if I square this, I get y squared equals 9 minus x squared. Bring over the x squared, I get x squared plus y squared equals 9. Now do you recognize it? I bet a light bulb went off, and that light bulb would tell you, hey, this is a circle equation, and I am dealing only with the positive half. From this circle, I can pick up my radius is 3. So let's draw in a circle with a radius of 3. So there's 3, 3 to the left. So I got negative 3, positive 3. Well, radius will stretch vertically upward as well. And we want to come through and draw in our upper circle. Our bounds were negative 3 to 3. Sweet. That means we're looking for the area that is contained in our semicircle. All right. It is a semicircle. So, hopefully your notes are not quite as messy as mine. This equals a semicircle. And radius, so it's a 1/2, so that we get the semi part of it, pi r squared. And R, we're going to evaluate where R was 3. So I'm going to end up with 1/2 9 pi. So how about 4.5 pi? That would be the value of this definite integral. Moving on. Alrighty. Example number 2. We're given a graph. It consists of line segments and semicircles, which will allow us to use many geometric formulas with confidence because I know that is a semicircle, even though it doesn't quite look like it. So let's just walk through these different, what do we got, about 7, 8 different definite integrals that they want us to evaluate. F of x is our function, and that is the graph we are looking at. So please jot that down. I don't see it anywhere there, but it should be there. So this is f of x that we're looking at. They want to know the value from 0 to 2 of f of x. So let's see, 0 to 2. 0 to 2 would be this region right here. This is our problem A, isn't it? Well, that's a quarter circle. So I'm going to do a quarter of pi r squared, evaluate it from, evaluate it when the radius is 2. And quarter circles, I only want 0 to 2. Proceeding onward, I have 1/4 of 4 pi. Oh, that's just pi then. Okay, we got that. But, I didn't even catch this until I looked back. Always good to check your work, isn't it? This area resides under the x-axis, so please tag on a negative on this. Negative because it was below the x-axis. So it becomes negative. Next, it says go 2 to 6. So how did I pick up 2 to 6? I looked at my bounds. And now I want this region, correct? Which is a triangle. So I'm going to have a 1/2 base times height, evaluating where our base is. How many units is the base? 1 unit, 2 units, 3, 4 units wide. And my height is 1, 2. It's 2 units high. So if I plug this in, I'd have 1/2 of 4 by 2. 8.5 is 4. And that is a positive region because it's above the x-axis. How about 0 to -4? I really should read that from bottom up. -4 to 0. And the bottom is smaller. That's good. We have that -4, and we're going to a larger value. So my integral is a proper integral. It's designed correctly. 0 to -4. Select a color here that we haven't used. We want this region, and I want this region. Well, this region I know is matching my first problem. This would be -pi. And then I just need to capture the area of the triangle. And the area of the triangle is 1/2, 1 unit high by 2 units wide. Looks like that's coming in as a -1. So this is going to be a triangle plus the semicircle, not semi, quarter circle. And that gives me -1 minus pi. From the next one, E, -4 all the way across to 6. -4 all the way across to 6 is essentially everything we're looking at here. So I'm just going to pick up my regions, -1 minus pi plus 2 to 6 was a 4, wasn't it? You might even want to jot 4 down as that. This region was -pi. And then you got your diagram all marked up, which is kind of nice. -2 pi plus 3 is our overall result. Ooh, the next one's interesting. They want us to absolute value the function. Well, what does absolute value do? Turns things positive. So, in a sense, I am trying to find a different color here. I'm going to draw in, let's see if we can grab orange. We haven't used orange yet. Okay. Draw in this new function. It would be orange, orange, orange. Because everything is getting turned positive. Must have been, oh, it was on text pen. So, everything is going to be a positive amount. What I'm going to do then is absolute value all of these different regions. -1 would be absolute valued. Minus pi. Oops, I'm going to do plus negative. How about absolute value that? Plus negative pi. Oh, hang on, guys. Negative pi. It's not liking my writing because it's not picking up the math notation on this text pen. All right, so there are our values. I took everything that was negative and made it positive. Now let's shoot in with an answer. I'd have 1 plus 3 gives me 4, positive pi, so 4 plus 2 pi. Final answer. Are you getting the hang of these? I won't take quite so long then to explaining. -4 across to 2. Well, that's going to be the -1, a negative pi, and a negative pi for a final answer of -1 minus 2 pi. 0 to -4 is a problem. This is an improper integral. It's not written correctly. Because we talked about how we should have lower bound on the bottom. So what I essentially want to do is flip this baby over. And when I flip it over, there's a property that says just add a negative in front. Then do the opposite of. Okay, so this will be a negative amount. -4 to 0. Opposite of, let's see, we had -1 for the triangle area, negative pi for the quarter circle. And I don't want absolute values. I do want just parentheses. And I've got my negative sign brought in here. So I get opposite of -1 is +1 plus pi. So how about a 1 plus pi? And finally, our last one, what do we got to do here? Ooh, this one's a tricky one. So it says take f of x and add 2. Well, we know when we add things outside of the function, not within x, but outside, we get a vertical translation. And in this case, we are going to move everything up by 2. This is a tricky one. So essentially, what I want to do, you guys, I'm going to clear my board because I'm going to take and copy this and show you that I'm going to lift it by 2 units. 1, 2. This now would be the new function, wouldn't it? And I end up with, you can see, a lot more positive region. But the easiest way to handle this is to kind of break this out separately. So I'm going to say, let's integrate, if I can draw, let's integrate from -4 to 6 of f of x dx. Remember the sum, the addition property of integrals? We can do this. And then we're going to sum -4, still the same bounds, of 2 dx. And this is that vertical translation going on, right? We have an answer from -4 to 6, which I am going to steal from prior. I think it's coming from problem E, or example E that we just did. And it was -2 pi plus 3. When I have a function that I lift by 2, I would have a horizontal line at y equals 2. And I'm starting it at -4, going out to 6. This would be the region plus a rectangle. This rectangle is how many units wide? Well, 6 minus -4 would be the width, and 2 high, so a 10 by 2. I pick up 20 units for this. That is the easiest way to handle this particular problem. So see if you can kind of interpret that. Walk back through that. We use properties of addition and integrals to break it off into two integrals. This was a problem we already knew. That see example E. That's how we got that value. This I thought about. It means y equals 2 is our function. That gives a rectangle that has an area of 20. So I grabbed 20, added the previous amount, and there we go. Sweet. Okay, last page of notes. I know this is kind of a long lesson here. Take a break if you need. I'm sure you already have. Let's go through the properties. They're not too hard. And then the bottom part of the page exhibits using these properties. So if f is defined at x equals a, then if I take an integral bounded from a to a of f of x dx, what would its value be? It would be 0. Why is that? Well, it's essentially, if I'm integrating at a to a, I end up with a vertical line at a, right? Because it's just going from a to a. There is no width. And if there's no width, there's no area. So that would be like a width of 0, essentially. So this turns out to be 0. If f is integrable on a to b, then if this implies that a is less than x, which is less than b, correct? That a is smaller. But here you'll notice they are reversed. So to reverse this back and get it into the proper order, with the lower value being on the bottom, I want to mix it around, and I do that through an opposite, a negative. So it becomes negative f of x dx. Okay? The additive interval property. If f is integrable on 3 closed intervals determined by a, b, and c, where c lies between a and b, then I can chop this up into two integrals. I can go from a to c of f of x dx and c to b of f of x dx. Because we have this continuity of the function between a, c, and b. And here's an example. So if I wanted to capture all the area from a to b, I could chunk it and make it two little areas and do a to c and c to b. So that is that property. If k is a constant, then I can pull k out front. I think we've done this already with just indefinite integrals. So k can be pulled out front. Addition and subtraction, we utilized that in that last exercise that we did. We can either add or subtract separate integrals. So we are given some rules of the game here. All right. So the rules are that an integral from 2 to 4 of x cubed turns out to have a value of 60. And from 2 to 4 of just x, the linear function x, has a value of 6. So they gave you the definite integrals values. Now, what we want to use are the properties that we just went through. Well, I see this constant, or a multiplier, and we know that we can use the property from above, this property, and pull it out front. So I can say this is 7 times 2 to 4 of x dx, which now allows me to slide over to my givens and do 7 times 6 and come up with 42. So it's all about making it so that I can utilize these rules of the game. I've got x cubed, so I know I've got to follow this rule. This one was set from 2 to 4. Oh, darn it, these are backwards, right? I've got the larger value on bottom. So we can switch that by utilizing this particular property. And that means in order to flip them over, I will use a negative out front. So 60 was the value for 2 to 4, and then I've got a negative. So it turns out to be negative 60. This next one is a vertical translation, is really what's happening. So I'm building a box really underneath. I'm going to chop this up. I'm going to use the addition subtraction property. Oh, I could even use the 2 out front, constant property. Add with it 2 to 4 of 70x. And you're going to like, hey, Ms. Apple, there's no rule given for 7, but we can think that one through. So x cubed was a 60, so this will be a 2 times 60, won't it? Plus 4 minus 2 multiplied by 7. That gives me 14. So I get 120 plus 14 ends with 134. Visually, if you don't like what I did here to get 4 minus 2, think of our function. Height of 7, y equals 7, and we are bounded from 2 to 4, and so I have 2 by 7 rectangle going on there. So that's how I did C. D, let's chop it up into 3 integrals. 2 to 4 of 60x plus 2 out front, 2 to 4 of x dx, so that I can match the x dx, minus 2 to 4 of x cubed dx. Turns out, similar idea, 4 minus 2, the width of our bounds, multiplied by the height. This would be width times height, plus 2. The linear function had a value of 6. The cubic function had a value of 60, didn't it? So I'm picking up 12 plus 12 plus 60, 24 and 60, 84. And finally, wow, this is a long lesson. 0 to 6, but I see a 0 to 3, a 3 to 6 of f of x, we want f of x. We can use that kind of transitive property is what I think of it as. I can go 0 to 3 and extend 3 to 6 f of x dx. And this is treated like a 0 to 6 one. So I pick up a 4 plus a 1, negative 1, gives me 3. 3 to 6, well, we want to use the opposite function. Because 6 was on the bottom and it was the larger value, so we got to flip her over. Negative of negative 1 gives me 1. Ooh, easiest one ever. If I have no width from 3 to 3, I have no area. It is that very first, oops, didn't go high enough, that very first one that we just did on the properties. So that C was 0. Negative 5 pulled out front, 3 to 6, f of x dx gives us, I'm looking over here, a negative 1, right? So negative 5 times a negative 1, positive 5. Awesome. I am sorry that took so long. Hopefully you did it in a couple chunks, but we did cover a lot of stuff. Please go on, look at WebAssign. That is your assignment. Let's see, looks like there's going to be 17 problems. Have a wonderful day.